Yeah, do you mind taking mine? Thank you.
We'll be getting started in just a minute.
Congratulations. Thank you. Nice to meet you.
Hello, everyone. Can you hear me okay? Great. I'm Thomas Sumner. I'm the managing editor for the Simons Foundation. Good afternoon and welcome from the International Congress of Mathematicians in Philadelphia. Thank you for joining us at this press conference. There is a press release with information about all of the winners on the Simons Foundation website. There should also be a link to that press release on the ICM 2026 homepage. At the bottom of the release, there is a Google Drive link with a collection of photo options. Today, we are thrilled to welcome International Mathematical Union President Hiraku Nakajima. Well, we will soon be joined, oh yes, there you are, Ulrika Tillman,
Yes, I already.
incoming IMU President, Fields Medalist Yu Deng of the University of Chicago, Fields Medalist John Pardon, who I believe will be joining us shortly, of Stony Brook University in New York, Fields Medalist Jacob Zimmerman of the University of Toronto, Fields Medalist Hong Wong of New York University and France's IHES, Abacus Medalist Cheyenne Oviskaran of the University of Washington, and Gauss Prize winner Yuri Nesterov of Belgium's University of Louvain. We'll be taking questions from journalists in the room, via the YouTube live chat, and via email. For those tuning in remotely, email is preferred. The email address is press@simonsfoundation.org. Again, if you're a journalist, you're tuning in remotely, email your question to press@simonsfoundation.org. For those in the room, my colleague Christina has a handheld microphone for you to use. Please identify yourself and your publication when asking questions. To get us started and to break the ice, I have a question for our award winners. What was your reaction when you learned that you'd won, and what does winning this prize mean to you? Let's start with Yu Deng and make our way across the table. Again, what was your reaction when you first learned that you'd won this award, and what does this award mean to you?
Thank you, Thomas. Yeah, so it's a really great honor to have my name listed after all those great mathematicians I've been always admiring. It's really important recognition of myself, of my works with collaborators, and the field of PDEs and also probability that I'm representing. So yeah, so I heard about the news, I mean, not the news, the official notification in January. At that time, you know, I was specific at that time. I was reading a novel, and I got an email from the IMU president saying if we can have a Zoom meeting at some time. I know because that was I kind of heard from previous people that this was around the time where these things are now the winners get notified, and I thought, okay, oh, that was it. So then I just kept reading the novel.
Yeah, thank you. I woke my wife up when I got this email to tell her that I think I got it, but then I started to have doubts. And so until we actually talked, on Monday. I was pretty stressed, which was nice for my wife because I stayed up with the baby, and she got to sleep because I wasn't sleeping anyways. And then when I heard it was a big relief, I was very happy. It's a big honor, obviously, getting this award for me and my collaborators, who I'm very happy are being recognized as well. Yeah, and I'm thrilled to be here.
So I received a call like half an hour before I have to give a talk, and so I have to try really hard to prepare for the talk and not to think about this, and then I hope my talk was okay. And it means a lot to me, also to all my collaborators. I remember I learned the news that Terry Tao got the Fields Medal when I was a high school student. I read from some math magazine. I was quite excited, so I'm also excited today.
I work at the intersection of computer science and mathematics, mainly like fields of approximation algorithms or analysis of Markov chains. I'm very happy for the recognition that this award brings to these fields. And I guess I also got happy, maybe people who I've worked with and people in my country who are suffering from war will get some happiness out of this recognition.
I learned about this prize in December 2025 from the President of the Union, Hirako, and of course for me it was very unexpected news. So indeed, in my fields, this is applied mathematics, so we don't get very often prizes from pure mathematicians, so it is really very exceptional. And for me, so all people here are very young, and for me, so this is different. For me, it was a kind of confirmation that the research direction with which I am busy during 50 years is good. So it is indeed something which people need. So it was really a very nice information for me.
All right, before we take questions from the room, I have a question from online, and that is for each of you. Could you explain the problem you worked on or what you did for an audience who might not have taken a math class since high school? Yudeng?
Okay, thank you. So, roughly speaking, what have been doing also with collaborators is basically to kind of connect the microscopic description of things, of the universe, to the macroscopic description. So specifically, think of the fluids, the gas. It's a continuum, like object, continuum quantity that is described by a bunch of equations called the Euler equation. On the other hand, like if you really kind of zoom in or microscopically, these things are made up from these tiny particles, and these particles they follow a separate law of interaction, the Newton's law. Okay, so then a kind of a long-standing question is how do you kind of derive these macroscopic behavior from the microscopic interactions of these particles? And this is something we have been working on. It's a long history with a lot of people making important contributions. And our recent work basically derived the so-called Boltzmann equation, which is intermediate step of this process for arbitrary long times. And this, combined together with the previous works, basically provides a way to connect this from this microscopic to the mesoscopic of Boltzmann, and to macroscopic complete kind of this bridging process under certain assumptions called the Boltzmann-Grasscaling law. And that's essentially it. Thank you.
So I work in number theory on something called the Andrew-Oort conjecture for a long time. And essentially, one way to view it is when doing number theory, you try to understand kind of probabilistically, statistically, what you expect to happen. And then whenever something unexpected happens, you look for geometric explanations for it. And the Andrew-Oort conjecture deals with Shimura varieties. There are these highly symmetric objects that are interesting because they can be viewed from a number of perspectives: algebraic geometry, differential geometry, number theory, representation theory. And the conjecture essentially says that if something, what's called special, which is a very unenlightening name for something, but something with a lot of symmetries, happens over and over again, satisfies an algebraic relation, there has to be a geometric reason for it. And what was nice about it was that a whole bunch of different fields came together, sort of started by my collaborator and mentor, Jonathan Pila, and Umberto Zanier, and a bunch of other people, bringing together sort of functional transcendence, in the end some Pierre Hodge theory, model theory, a lot of other fields. It's really nice when a bunch of subjects come together on a concrete problem like this.
So I work in Fourier analysis and geometric measure theory. A problem that lies in the two fields is the Kakeya set conjecture. It is about if you have a set that contains a unit line segment in every direction, then how small can the set be? The conjecture says that it should have a 4 dimension, has the maximum possible dimension. And fortunately, joined with Josh Zhao, we proved the 3-dimensional case based on a lot of prior work by Katz and Tao, and also many other people.
I use tools from mathematics such as probability or polynomials to design algorithms for some of fundamental tasks in our daily lives. One of the problems I've worked on is called traveling salesperson problem, which is, say you have a number of tennis balls on a ground and you want to go the fastest way to collect them all and put it in a basket. How would you do it? So usually the approach that I think about is that I want to design an algorithm that can beat any adversary. Think about an adversary as someone who is competing with you, or maybe it's a company who's trying to sabotage your work or something like that. So it turns out that if you design an algorithm which always follows a fixed number of sequence of steps, then it's way easier for an adversary to maybe engineer an instance and make your algorithm fail. So one thing I do is that I use randomness and make these algorithms randomized so it's unpredictable or less predictable. And it makes it much harder for an adversary to engineer an instance to beat you. So you can prove that your algorithm works in the worst case.
My field is the development of efficient optimization algorithms. And today, many people in daily life, they see more and more examples of applications of optimization algorithms. Maybe the easiest example is the navigators, so for choosing the shortest path in the transportation network, which everybody is using today. And just imagine that now it takes, I don't know, a couple of seconds to generate the optimal route, but imagine that it would take 2 hours, yes? So then our life would be completely different. Nobody will be using it for actual navigation. And for us, this is exactly the goal. So for existing optimization problems, to reduce the computational time as much as possible. And this defines the applications and many things. And what is important, so we're not interested in the heuristic algorithms. So we want to prove something about algorithms with performance guarantees, and after that apply that in the real life applications.
Well, thank you all. I think we can now turn it over to questions from the audience. Oh yes, right in front.
Hello, my name is Christoph Drösser. I'm working for Neue Zürcher Zeitung and Deutschlandfunk in Germany and Switzerland. I have a question for the 2 Chinese winners, Hang Wang and Yu Deng. I think it's a great success for Chinese mathematics that I think you are the first winners who had their training in China, not in the United States or Europe. And so the first question would be, how did you think this came about? I saw that almost the same number of mathematicians is trained in China as in the US. But on the other hand, you are going, in your careers, you went to American or French universities. When will we see people going to Chinese universities to do groundbreaking work?
Okay. So thanks for the question. Yeah, so I think China has, I think at least I haven't had too much contact with China like recently, but I heard from my colleagues in China and my collaborators that really the Chinese universities is getting much better today, and I believe given the the huge investment of the country and all this, I believe this trend will continue and they will get better and better. So I think you see, even in the last few years, there has been really good works done by Chinese mathematicians. I mean, including the mathematicians like in Chinese Institute. So I think it's an obvious trend that they're going to get better. I mean, I don't know if I can predict like when there will be some something like this from Chinese Institute, but I think it's the trend is clear.
I feel very honored to be together with Yuden as Chinese born citizen who have got the medals. I think it's already happening, and that the mathematicians in China are already producing great work. And also, I have a lot of collaborators just moved back to China. Like Josh, my collaborator Josh Sa is now based in China. And I believe they will just continue making the math better there.
Thank you. Other question from the audience? Oh, there's also a request from people watching remotely to be a little bit closer to the mics. I don't think they're as sensitive as we hoped they would be. Yes.
First of all, my name is Ziqian Yang, and I'm a student from China now studying physics in the United States. And first of all, I would say congratulations for all of the medalists, and thank you all for your great works. I think our textbooks will add more chapters because of your works to study more. And I have a question for two Chinese fields medalists, Professor Deng and Professor Wang. So as a student, could you please give us some advice for study mathematics, especially for students like me in the college or both undergraduate and graduate school? Thank you.
Yeah, I mean, for students, I mean, I think you have a lot of possibilities. I think it's good to try to explore kind of as much as you can, try to find what you are really interested in, what you're really excited about, and then you can start learning, start working on it, start playing with it, and enjoy. I think there are several interviews before, and I always say this: do what you like and enjoy what you are doing.
I think one lesson I learned in the past is that as long as in the end you get something, it doesn't matter how much time it takes for you. Maybe it takes, for other people, maybe it's faster, but for you it's slower. But it really doesn't matter. So I think take your time.
And I have a question for our IMU presidents, and that's, why do you think the Fields Medal has become the top prize in mathematics, unlike something like the Nobel Prize, where it's for discovery or for a lifelong contribution? The Fields Medal is a little bit different. It's for only people under the age of 40, and it's for future contributions as well as past achievement.
Yeah, I believe this is a historical reason. So Fields Medal started in 90, I don't remember exact year, but before the World War II. So all other prizes in IMU or other mathematical prizes are established afterwards. So the IMU, the Fields Medal have the longest history among the prizes in mathematics, and that is the reason. And also, when I choose this recipient, I make a call of the nomination to the mathematical community, and I receive many, many nominations. That means that the mathematical community really likes this Fields Medal, and this is somehow the idea of the original idea of Fields somehow understood by community.
Question for the room? Yes.
Maybe.
If I just add, I mean, the Fields Medal is also, I think, an exciting one because it looks forward. It's not just looking back on somebody's life achievement, but it looks forward and the excitement that might be coming even. So I think that's...
As a math fan and a parent, what were the single most changes that your parents did in your environment and your structure to help you move to your success and be a thought leader? Fields medalists?
My parents were very encouraging always. I'm not sure I have a great single answer to this. They gave me puzzles as a kid, and I really liked that. And then they would just sort of seek out other ways to allow me to continue to engage with math. So we tried tutors at some point. I went to various clubs. There were certain schools and programs. There was no sort of one thing, but I think it was mostly one is letting me spend my time sort of doing math, which maybe a lot of parents would do, I'm not sure, but being very supportive of that, and also just continuing to try to engage with me, which is not easy, to be honest, as a parent. I mean, I would have an easy time if my child liked math, but if they liked some other subject, you know, I can imagine the sort of struggling to get oriented and figuring out the landscape. So that's something I'm grateful to my parents for in particular.
Sorry. Yeah, so my parents, I think mainly my father, he was really liked math, and he was in the 1980s, I believe he was of one of the earliest Chinese math Olympiad contests. I don't exactly remember which one, but yeah, he was really interested in math. And when I was a kid, he would we would go for hiking, and he would give me some questions combinatorial questions. And I remember one time it was about the recurrence relation. One time it was about this kind of famous monochromatic triangle problem. And we had discussions, and sometimes we were able to solve it. And it was really nice experience. And I think that's kind of shaped my childhood. That's made me. It was one of the main reasons that I got interested in math, as a kid, and then later on, leading to all these stories.
Would anybody else like to speak? Otherwise, we can move on.
Well, I'm going to say that I'm very grateful for my parents that gave me a lot of freedom. I basically could do what I want to do. But something they did try to say is that maybe I should be better. I should try to be good at something I want to do.
Yes.
Thank you very much. I have a question first to Hong Wang, as well as other people who feel comfortable to answer this question. We learned that you was going from mathematics to architecture and then going back to mathematics. I have a question. Could you describe some situation in which your mathematical way of thinking can cause problems or misunderstanding with real life? So it's actually a question to everybody who want to describe some concrete situation, because not everybody have mathematical way of thinking.
So just to make sure I understand the question, it was like, when does mathematical thinking cause a problem in real life?
People misunderstand you or just have some...
I'm not sure if this happens in real life. For me, it doesn't cause a problem.
Well, I think in general, when we want to convey something, we will convey it very precisely. So I think it's most cases probably will not cause a problem.
And maybe to follow up with Hong Wang, you mentioned your experience with architecture as part of your career. And I was wondering, was there anything you took from that experience in architecture to your math?
I guess I learned that I'm more interested in math.
Great answer. Anybody from the room? Yes. Christina's making her way toward you.
Hi, my name is Andreas Dillies. I'm a reporter at the Odyssey Media Group of Clark Central High School. And I wanted to ask, a lot of young students now who are studying math and the sciences, they've been brought up with artificial intelligence. They see that ChatGPT, Claude, Gemini can now solve almost all of the problems in their high school classes. And now we're seeing that artificial intelligence is tackling harder problems. We saw the Jacobian conjecture in 3 dimensions was proved wrong a couple days ago. We saw artificial intelligence tackle a problem of Erdős a couple months ago. What would you say to students who are feeling that their place in modern mathematics might be shrinking and they're unsure of their future in math?
Yeah, I think they're right to be paying attention. I think the world is changing, and the math profession as it exists now, I bet we all have different opinions. I'm speaking for myself. I don't think it will exist the way it exists right now, and I think people are right to pay attention. I would say that people tend to get sort of nihilistic or despondent. It's very easy to become distraught at the big changes that are happening if you place your value in something which is going away. But I would encourage people to, first of all, not give up on themselves, to keep learning and improving themselves, because you don't know how the world will turn out. And however it turns out, the safe thing to do is to invest in yourself. And so to keep learning, to keep being excited, to keep figuring out the world, and also to engage with AI, to keep engaging with it, because it's going to be a big part of our world going forward.
Yeah, so I think it's I think it's there's a clear trend that AI is going to kind of change the mathematical research by a lot. But I'm probably kind of on the more optimistic side that the AI is going to be kind of helping mathematicians instead of replacing them. Like what we have been, what we may expect in the future is that the mathematicians will come up with new theories, new ideas, new frameworks, and the AI is going to do some of the technical details. AI will get stronger, but then will redefine what is technical details. In any case, I think at least I believe that the way we study math will change, but the joy we get from studying math will not change. That's my opinion.
I think I can give one advice to maybe high school students or earlier, which is that I think like even now elementary school students learn how to multiply, even though they could have just used a calculator, tens of years ago. So I see my kid learning how to multiply or divide in the last 3-4 years, and there is reason for that. I think if you want to get good at mathematics, you need to start from some principles. You need to understand the principle, even if you can do it with AI. And that's something I like the younger generation keep doing. Like if they keep using AI, they never understand the basics. They never get strong foundation, and they never become a successful mathematicians down the road.
Yeah, and I also want to add actually that you shouldn't think that the AI which exists today, it is just its final version. So AI is going to be developed, and for its development we need mathematics. So it is just the opposite. So with artificial intelligence we have a lot of new research directions which are very interesting and which need mathematicians.
And Yuri, your fast gradient method is part of the reason why we have modern AI. And I was wondering, how does it feel to see over the decades that idea become so important?
It is not actually the reason. So the consequence is that we can get the answers from AI in a reasonable time. So without this algorithm, it would take, I don't know, much more time. But what is important now, actually, that indeed artificial intelligence needs optimization. Artificial intelligence, if you apply to different fields, so you need to create some mathematical models which must be solved by optimization methods. And therefore, for our field, this is indeed the golden age. So in the coming years, we will have many interesting formulations which need efficient optimization algorithms. And also, so mathematics is going to penetrate much deeper to all other sciences which we have now, which are considered inexact and so on. In many of them, we should develop the mathematical models and develop methods and so on. So it is a really important time.
Any other thoughts? Or we can take a question from the end over there. Oh, yes, and everybody can just kind of push their mic in while we have a little bit of moment.
Hi, reporter from Xinhua News Agency. Congratulations for all the winners. Actually, my question is for the president and the incoming president. So, this is the first time for the two Chinese scientists to win the Fields Medal. Yeah, it's the first time. Very important. They take their essential part of the education in China. So that's why we are so focused on this. So what's your take on their achievement? For their achievement. Also, I want to have your take on the China's mathematics study in China worldwide.
So, quick answer is that we don't care. Because I mean, when in the committee, I was the chair of the Fields Medal committee, and when we discussed the accomplishments of recipients or candidate recipients, we never consider their nationalities, and maybe that is a part of the discussion on the mathematical education. That is not really among our interest. We only look at the recent accomplishment of the candidates. That is usually done in the current institution.
Well, I don't yet have experience with this particular committee, and Hirako, I think, said exactly what I would expect, that we try to, one tries to honor those who have done the work and come to an agreement within the broad committee to make sure that we consider everybody from all areas of the world, of course, and all the nominations that come through different national societies, etc. And then you try to make a decision purely on the mathematics. I guess another thing that you try to do is that to have a committee that is both knowledgeable but also representative of different fields, of different areas, and possibly even cultures. So that is, of course, something to ensure that one doesn't oversee somebody.
In the back there in the green.
Thank you. It's Rachel Thomas from plus.maths.org. I had a question for Cheyenne. You're recognised in part for this new approach to the travelling salesperson's algorithm, and starting with a random spanning tree where they previously started with a sort of more fixed approach. What made you think of that? How did you know that would be a good approach? Were you surprised that it worked so well?
So again, like I said a few minutes ago, if you start with usually a fixed solution, it's way easier to construct instances that your algorithm fails. It's like when there is this adversary, so when you're designing an algorithm, you think of there is this adversary who's trying to fool you. So if your solution is fixed, adversary usually can beat it. So what we thought about was that can we come up with some probability distribution of random instances, in this case so-called random spanning trees, that are sort of as good as what you would get deterministically, but now you have randomness helping you avoid these certain engineered instances. And that's where we use a lot of mathematics. For example, something we do is that we look at the probability distribution that has the maximum entropy. That means that it is as random as possible among all probability distributions that you can think about. So I guess I was hoping that this works for many years. Any instance that I would construct, the algorithm seemed to work, but I didn't know how to analyze it, and it took 10 to 15 years to analyze it.
Right, before we move on, just a reminder, you can email in questions at press@simonsfoundation.org, and I think we have a question in the very back there.
Hi, thank you for your time. My name is Mrinal. I'm not in academia. I work as a macro trader, and pure math is just an interest. And back to the topic of artificial intelligence, one way it has impacted the life of people who are hobbyists is that it gives us a better intuition on the complex problems that you guys work on. So to build upon that topic, I wanted to understand how you guys, and this is for all the fields medalists, how do you see your work evolving in terms of framework building versus technique, which these tools would probably assist a lot in? And as a follow-up to that, specifically to Dr. Zimmerman, my interest is in number theory, my hobbies are in number theory, so more on that. You imported areas of math which are pretty different, right? Like Hodge theory, logic, in order to arrive at discoveries in number theory. Do you think AI has this edge where there is where you're not localized to one specialty, so you're able to kind of go in depth to a number of areas, and hence come up with relationships and discoveries which are not that, which would not be that obvious to a human who's specializing in one area? Thank you.
Yeah, thank you. First of all, yeah, I mean, a lot of the stuff that I imported, I learned from collaborators, and I followed up on traditions. I think there's this, I just want to make sure that we don't fall into this trap of thinking one person who gets recognized does everything themselves. As all the winners have said, we've all benefited a lot from collaborators and previous work by often tens or hundreds of people. In terms of your question regarding to AI, there's definitely an edge AI has that it can look through things very quickly and operate very widely. You know, given mathematician will be an expert in one subject, then probably very knowledgeable in a few others, and then several others where you have some idea, but you're relying on your collaborators and now on AI to get oriented. So one way that I use AI the most is when I'm trying to digest a paper or another subject, and I have sort of a vague idea of like, hey, does something like this work? And I sort of write down some intuitions that I have, maybe analogies from other fields, and the AI will very quickly help me get oriented. Now, these systems are evolving extremely quickly. If you had asked 2 years ago, they would have been more or less useless. 1 year ago, useful for a very narrow range of tasks, and now extremely useful. So it's hard to take a snapshot in time and say how useful they are, but the general trend for my own work of using AI to very quickly get oriented in other subjects and other papers is probably the biggest way that I've been using it for research.
Let me answer a little bit the AI question. So in my most recent paper, which was on arXiv just a few weeks ago, we have been using AI as kind of, in various aspects. So one example was, we had a technical question, like we kind of didn't know what to do in the beginning. We asked AI a little bit, and it didn't solve the problem, but it points a specific lemma about the summation over, weighted summation over all the spanning trees that we were not aware of. And then we learned that lemma from AI, and then in the end, in the proof we produced on our own, we actually relied heavily on that lemma. So you see, this is an example where AI is much more knowledgeable than human that we can benefit from. And another example was there was again another lemma, like I actually spent like 5 days to solve it, and then as AI, it produced a very simple proof, like a one-page proof, like within 1 hour. Okay. On the other hand, that proof we're not able to generalize that. It wasn't generalizable, so it didn't really use that proof in our paper. But at least it shows something that the AI can provide like nice ideas. But you also need to judge for yourself, make your choice how you are going to use it, how it's going to help you.
Anyone else? Otherwise, I have a question for the whole table. Do you have a mathematical hero? Maybe somebody you go to when you're struggling to look up to.
For me, this is John Bogan. So I never met him in person, or maybe I was in the conference honoring him in 2016, but I don't think I really saw him in person. I read his papers. His papers were very, very nice, extremely deep, and also extremely hard to read. Yeah, so I think in 2015, like when I graduated, I got an invitation to spend like 1 or 2 years at the institute. I could have met him if I decided to accept, but then at that time I decided, okay, I want to move to big cities, so I didn't. It was really a pity. But anyway, so I really admire his work. His his work not only the breadth but also depth and with everything he did. So I hope maybe with the thing. Okay, so he passed away in 2018. So I hope like with the things I did, after that years, maybe I can get kind of a little bit closer to him in some specific area maybe.
There's a lot of mathematicians that I admire. I wouldn't say I can single one of them out. Certainly my advisor, Peter Sarnak, has been a big influence because he seems to be involved in everything in the universe. And when working with him, I would take effort to make sure we were at an isolated place so that he couldn't be interrupted by the many hordes of mathematicians who wanted advice.
It feels like I'm combining the previous two fields master's answer, but it was my true answer. It's my true answer. So Jean-Paul Gain is also my mathematical hero. I really like his work, and it's kind of so. Sometimes in math, it's like you are going on a difficult hike, and some of the tools that Jean-Paul Gain developed feels like something that could save you on the very difficult hike. And also, I really like my advisor's work. I like his taste, and also, I like how patient he is towards his students and postdocs, and we all very grateful for what he has done for us.
I guess, yeah, it's similar for me. It's hard to choose a name. Of course, my advisors, I had two advisors, Amin Saberi and Luca Trevisan, who Luca passed away last year, unfortunately, but they really had a big influence on me getting into where I am right now, so I'm very grateful for their support.
Yeah, I think I should say that it is Gauss actually, but
perfect.
But more recent time, this is of course John von Neumann, so the person which created the modern computational mathematics and computers and many other things.
Thank you all so much. A question in the green there in the second row.
Yeah, for whichever medalist can answer it. I'm Joseph Hallett, Scientific American. What's a breakthrough, ongoing trend, something you're excited about in math from the last 2 years that is not represented on this stage? And don't say AI.
Yeah, so one thing I really like is this, well, it's not AI, but it's a use of computer. It's computer-assisted proofs like in the field of PDE. So it really kind of allows us to do many things that was not thought of as being possible. So for example, there was this very great work of the singularity formation of Euler equations, and there's more recent work on the non-uniqueness of Laurier-Hobbs. So the thing is that like by using this computer-assisted proof, you can have much more flexibility, because previously you can only kind of look at a specific exact solution, and you look at the perturbation, stability, and so on. But really now with this, with this computer system, you can really treat the errors, rigorously, and then you don't need to look at the exact solution are very rare, and if they happen, it's usually very hard to analyze. But if you can do kind of numerics, well, there are a whole lot of literature on numerics, and then you can do something, very precise. And once you can control the error term, then you can really do many things that people wasn't just. People were kind of blocked. Like I think it's really. I mean, it's really like a really real breakthrough that's occurring kind of in the last few years, and I'm sure it will produce much more great works in the future.
Pretty representative crowd. My brain is blanking. I think there's a lot of great stuff happening in representation theory and number theory, from the geometric Langlands program to all sorts of other stuff that I think the stuff with condensed mathematics and such, that I think there's some new foundations for math that it's hard to say exactly where they fit at the moment, but I think it's really exciting work.
I have a question from online, and this is for our IMU presidents. The question is, can mathematics and the institutions that support it truly remain insulated from politics? As geopolitical tensions rise, there's issues that arise because of that. Are you concerned that the mathematical community may become fragmented along national lines? Feel free to take your time and think about it.
It's too difficult question, so maybe I can answer afterwards.
Yes, one could answer afterwards probably. But I think it is important that we try to see the unity, and I think some of the words and comments this morning were very strong in that direction, right? I mean, mathematics is a universal language, and we can work on problems together and try to be beyond geopolitical problems. Of course, as an international organization, you immediately step on toes by just being international and deciding, which nations should be part of the organization or something. So one has to acknowledge that and work carefully with the concept and within the union and with the people who are involved. I think the IMU in particular, we are here for the mathematical community. We are not here to do politics. And how to support the community best at every stage should really be, I think, the guiding question. Of course, individuals will take different conclusions on whatever the situation is, but as a community, I'm trying to maybe lead the community within the IMU. We have to consider what is best for the community, not immediately, but also in future. So I think that's a very important thing.
Questions from the room? Yes, back left.
Hi, thank you. My name is Agatha Timon. I'm covering the ICM for several Spanish outlets. I have two questions. The first one is for Zimmerman. I would like to know, because your results touch the Hodge conjecture, could O minimality be used to solve this problem? And if someone eventually resolves Hodge conjecture using that, what would that mean to model theory?
Oof, that's a great question. Touch is the right way to put it, because I feel like I've put a lot of effort into working on various simple cases of the Hodge conjecture, which are still too complicated for me to have done anything on. It's a hard problem, and I think we don't know which way it lies. I don't know if you polled people, if they thought it was true or not. Do I think omnimality could help? Maybe. I mean, Hodge conjecture is one of these questions where, at the end of the day, assuming it's true, you have to produce a cycle starting from an algebraic variety. So it's similar to questions where you got to make a rational point. You have to make a variety. You have to make something. And omnimality at the moment isn't really the tool of choice for that. For your second question, so yeah, I guess I would be, at the moment I don't see a way, but I also don't see any way. So, maybe that'll be the way. For your second question, I do think model theory doesn't get enough credit for its results, because model theorists and model theory in general thinks in a very different way. I remember when I got into this field, I used omnimality as a tool. I learned to from Jonathan Pila, and then I got invited to these conferences, and boy, the questions they asked made no sense to me. It took me so long to figure out how one could operate like this. But then eventually you start seeing the beauty in the madness. And what happens a lot of the time is that model theorists will achieve some breakthrough in some other field, and that field will come and sort of scoop it up and rephrase insights in their own language, and then sort of conclude, well, model theory wasn't really necessary. And I think that's a little bit unfair. So I'm really happy to see that recently model theory has been getting more credit, and I hope that the way of thinking that model theorists present becomes more present in mathematics, because it's really quite impressive and useful.
Thank you so much. My second question was for Wang. The Kakeya conjecture is still open in dimension 4 and plus. Do you believe there's a clear pattern across all dimensions waiting to be found, or is dimension 3 like a special isolated case that doesn't generalize it, doesn't generalize simply?
Thank you for your question. That's also a great question. I think so. Some of the tools, like the framework we set up for the three-dimensional case, might also be helpful to understand what's going on in higher dimensions. But the higher dimensional case has this extra algebraic abstraction, and then some of the tools from like different fields of mathematics, for example, Leelavati, might be helpful. It's hard to predict how difficult it's going to be to understand the Kakeya sets in higher dimensions.
Yes.
I'm Carmela Padovich-Callahan from New Scientist, and my question is about sort of the historical context of a lot of your work. Like some of the work cited go back to like Hilbert's problems or the Gromov question. The Kakeya conjecture is also a couple decades old. I wonder how you think about sort of the pace at which mathematics has been tackling these foundational questions, and where you think the next set of questions that will be equally influential may come from. You know, will we eventually run out of these questions? The Hodge conjecture is a millennium problem. Like, will we eventually run out of these old questions, and what are we going to do afterwards? I know I'm asking you to predict the future, so catch as much as you want.
I don't think math is in any danger of running out of questions. I think what makes a list of questions sort of interesting to the public is hard to predict, but I'm quite confident we're going to have questions for a long time.
Yes, and the plus, the existing questions are already hard enough to solve, and they will probably take mathematicians like another few decades, or if not a century, to solve these problems.
All right, we have another question.
Hi, I'm Kai Williams from the Substack newsletter Understanding AI, which might give a clue into where my question is headed. But I was a math major before I got into reporting, and sometimes I feel split when I read kind of AI and math news, because the AI side of me is like, that's interesting. The math side of me is like, I feel like I'm getting the less of the math in this coverage. And like, I'm curious if anyone at the table has opinions on what has been lost in public conversations when we're talking about AI and mathematics, and if there's anything the like mathematical community could do better on their side to like help foster this conversation.
I mean, I think it's very hard to digest what's happening right now, is why the discourse has been, you know, maybe seems worse around this issue, maybe is worse. It's a new phenomenon. There's a lot of issues. The rate at which things are being produced is very high. That's sort of atypical. It's a little bit hard to separate what's sort of been called AI slop from things of content. Lean promises to help with that formalization a little bit, but we're not there yet. So I think there's a bunch of things to grapple with. And also I want to, you know, like before when I said I think there's a real change going on, and people are on different sides of it, even on this, you know, panel, very clearly. So in terms of what's going to happen, in terms of doing better, I do think it's important for the math community at sort of all levels, the levels of departments, universities, publications, the IMU, to as quickly as possible try to get ahead and try to grapple with how this will affect the profession in the future.
Maybe I can add, I mean, I completely agree with that. I'd like to add that actually we should remember AI ultimately is mathematical science as well, right? So a lot of it is at least. One question we sometimes, maybe in this particular community, forget to ask is that how can mathematics help AI? And indeed, some of the questions, the new questions might come actually from that new area that we need to tackle within mathematics. So I think that is a direction we should really grapple with as well.
maybe something I can say. I think in my experience, maybe 90 or 95% of AI contribution to mathematics has been in finding counterexamples to many conjectures. And I think there are many reasons for that. For myself, there has been a number of conjecture I was trying to prove, but I really didn't try to actually find the counterexample, and AI did it. So it's like, it makes it way easier to find counterexample because it does the coding, it does all sorts of special cases, small cases that it would otherwise take me maybe weeks or months to code up. So that's one reason I think maybe we're now seeing a flurry of results in the last few months, so maybe it dampens down. But so far, I haven't seen anything, at least to my knowledge, deep new theories coming out of this. And I'm eager to see if we're going that way.
Actually, so I would like to add a couple of things. First of all, so we shouldn't take AI as a single, let me say, person. So there are several AIs with different performances created by different firms and yes, with different capabilities. And from this version, so we get different answers. So it is the same as with people. And also, for me, so AI is still, and maybe it will be always like that, a kind of a technical tool. Just imagine you want to put pieces of puzzles at the right places. So this is the technical problem. So it may be very difficult for human being. It may take a lot of time. And for AI, this is possible just because all pieces of the puzzle are already there. And we know that. So we can find the solution. So AI can find indeed the existing technical solution quite easily. It is much more easier for them. But it cannot create new things, really new. So the things which do not exist now in all these databases and so on. So this new creative activity is still the task for the human intelligence, not for artificial one.
I would say one technical thing about AI is that now AI can produce proofs, and we know that it can actually correctly solve hard problems. But then like a random proof produced by AI, we still cannot fully trust it. I mean, it has been, in this first proof, second round, I think it asked this kind of short proof, like an 8-page proof, to ask AI to do it. And, the successful rate was like a little bit more than 50%, if I remember correctly. And this is a problem because AI can produce like many proof, and if you need to verify, every one of them, by human, this is a huge effort. And so, I mean, of course, there are, in this direction, there are these attempts to formalize a proof in Lean, for example. But as far as I know, like these two directions are kind of, they are kind of, people start to connect them, but they are still not yet like very well connected, and this is something that maybe, something that maybe we can expect in the future. But yeah, this is one comment I want to make regarding this.
All right, let's take another question from the very front here.
My name is Keiichi Nakane from Yomiuri Shimbun in Japan. My question is for President Nakajima. The information regarding this year's laureates was leaked before the official announcement. And how do you feel what happened? And do you know why it happened?
Yeah, I prepared the answer to this question. Thank you very much for asking. So today's ceremony was the first and only official announcement of the fields medalists and other prize winners. So winners themselves and prize committees and also the other members of the executive committee kept their names confidential until today very carefully. So we circulated names to medalists, but with embargo. So until now, they should not announce to public. And we don't know. We know some rumors, but we don't know the source of rumors and why this happens. This is my answer.
Thank you. Any other questions from the room? Yes, back in the yellow.
Hello, I am a PhD student in math, and I am wondering, I find it very challenging to work on math because I get very, very focused, but it becomes hard to have a well-rounded life at the same time. So I'm wondering what your favorite hobby is outside of math, and maybe, if optional, make a comment on how to lead a well-balanced life while doing mathematics.
Well, I do improv comedy, as my video showed, which I find balances me out a lot. Yeah, math is hard. I mean, I tell this to all my students. Math is hard partly because we get rewarded so infrequently compared to, I think, most other professions. Not that I'm an expert in that, but in math, you know, on a good year, you have maybe 5 results if something incredible happens. And so that's a result every like 2.5 months. And most of the time you're stuck, and you have to learn to create proxies for yourself that make you happy. So, you know, one thing I do, which I think others do as well, is on a day when I have an idea, I try it and fail, I'm very happy because I ended up doing something as opposed to looking at a piece of paper. You end up measuring progress by your own knowledge, all sorts of things like that. And still, I mean, even now, sort of so far removed from my PhD, I had a year recently where sort of nothing worked. And it's pretty sad when nothing works. You know, you learn to handle failure, but 1, 2, 3, 4 projects, and then you start thinking, oh boy, this isn't going well. So I think it's separate for every person, the sort of battle with becoming overly focused, not having time for other things. I think it's an exploration. I think be kind to yourself and talk to other people. I think too often it can feel like you're not doing enough, and that leads to being more insular, which makes the problem worse. So I think seeking community in seminars and other mathematicians and outside of math is helpful. I know that's somewhat generic, but I hope there's some value in that.
All right. I have a question for Hong Wang. And in the video that played during the opening ceremony, you mentioned that you had some difficulty with mathematics when you first went to university, and obviously you've gotten over that. And I was wondering, did that struggle help you at all later in your career as you're tackling these very difficult problems?
Thanks for the question. I think it helps me psychologically because at that time I got used to myself not being the best. And then so I feel more comfortable when I work on a hard problem and it didn't go well because I think I'm used to it. So this makes me feel like I could keep going a lot more.
Hope for those of us who struggle with math sometimes. All right, yes, question in the front. Christina is making her way toward you.
Thank you for answering my question, the parenting question. I have 4 kids. As the CFO of a single-family office in New York and for LinkedIn, what is next for each of you? And do you think quantum computing is going to change how you do math? Because you won't be waiting as long for the AI to get back to you.
So your question is, what is the next step for each of us? Yeah, so there are still a lot of things like in the direction I'm working, essentially like, let me describe it as general, like critical problems in PDEs, SPDs, in all these kind of things. There's still a lot of open questions, and I think our methods will probably work for some of these problems, at least I hope so. For quantum computing, yes, I mean, if it really, is realized, with very in a very practical way, I think it would really mean a lot. Everything will get much faster, and calculations and so on. So it will be a very good thing. I mean, we're not seeing it now, but maybe we'll see it sometime in the future. So
I don't have much knowledge or opinion on quantum computing, besides the fact that it seems cool. What's next is I'm going to be, I've already started pivoting towards AI safety in my career, using math for AI safety and otherwise. So I'm preparing a list of resources for mathematicians to pivot to the subject, because I think it's a very important subject that I want not just mathematicians, but lots of other people, but mathematicians in particular, something I know about, to have a bit of a role to play. I'll be starting a position at OpenAI in their safety division very soon, so that's what's next for me.
I'm still like trying to figure out what's next to me.
I think for me, it's the best time to do mathematics. It's like I can, like with the use of AI, I can publish, like I can solve many of problems that I've been stuck for years. It's like having lots of cheap research assistants working at a very fast rate. It's like, yeah, so it's very exciting. And the community is moving at a very fast pace. I have hard time catching up to all people. But about the quantum computing, I think we are very far from actually seeing that, make an impact in our life. Like even if it happens, it's very far that it leads to maybe faster AI computation. I don't think we will see that anytime soon, maybe at least in the next few decades. I wouldn't expect that.
In our field, actually, the most challenging problem is the construction of efficient algorithms for neural networks. So neural networks are very successful now in different domains, but up to now they remain on the heuristic level. There's no theory which can tell us what is the complexity of these problems, what are the efficient methods, and so on. And of course, this is very important to understand what happens.
All right. Are there any other questions? Yes, in the front here. Oh, way in the back, sorry. Let's go there. Spread around the love.
Hi, my name is Jonathan. I'm wondering which directions or which answers or which questions you're expecting your work to answer in the way like, oh, I'm very excited for someone to use my theory or my methods or in this particular field. Like it doesn't have to be necessarily pure math, but it could be applied math, engineering, and science, and you'd be like, oh, or maybe yourself be like, I want to use this work to answer all these questions or anyone else, or directions in general.
Yes, for me, I think I answered this in the previous question. There are these lots of still open problems in this in the description of in this so-called critical theory, which I hope the method we have been developing with collaborators Zhang Hanni and Xiao Ma will be useful in answering all these questions. Like we are, in my recent paper, we are starting to work on some problem, some critical problem on SPDs, and I believe this is just a first step.
I'm very happy whenever anyone uses my work for anything, because first of all, it feels nice, and it also gives me a bridge to learn about that new thing. The questions I'm most interested in are ones that aren't particularly famous or well known. So if that was part of the question, I'm curious for developments in torsion in class groups, something called Zhang's conjecture, which is my favorite problem, but it's not particularly well known. And if something I did could be helpful, which I was, I've tried and failed. So then if somebody else picks it up and succeeds, that's kind of like I played a role. So that would be cool.
So some of my works are in this field of analysis of Markov chains. And this field has like enormous applications across many areas of sciences, like physics, social science, chemistry, and so on. So it's often, there is some quantities that you want to measure. And what you do is that you simulate a so-called randomized algorithm called the Markov chain. And you run this algorithm, and then you hope that by running it enough, it works, it gives you, the right estimate of what you're interested in. And usually for practitioners, there are questions that how long you should run this algorithm before you stop and claim victory. So one of the things we do as mathematicians, we actually prove theorems saying that, okay, maybe 100,000 step is enough, you should stop right there. So one of the things I did was that I came up with some new tools and techniques to say how far you should run these Markov chains. And that's something I'm expecting to see maybe a lot of applications beyond what I'm doing these days, like in other areas of science.
Yeah, I am working in applied mathematics, and in our field, so we are much more flexible as compared with the pure mathematicians. Pure mathematicians, if you have a problem which is formulated, written once, you are not allowed to change it at all. So you need to solve it as it is. It doesn't matter how much time it takes, 1 year or 100 years. So the question is posed, and you have to answer it. In applied mathematics, it is not that. We have time constraints. Okay, the question should be answered either now or in 2 or 3 years. Nobody will be interested in that. And therefore, so for us, it is possible to play with formulation. So if we cannot solve some problem, so we can change it. We can somehow adjust the parameters or maybe functional dependencies or something like that, having in mind the abilities of numerical schemes. And then, so we get the problem which is solved, and we can speak about efficient methods. So such things should be done for sure with the existing formulation for the neural networks, which in the current form, so they have non-convex, many extremums, and so on. So this is maybe the first thing to do in this direction.
Well, thank you all so much. I think we're going to wrap up now. I'd like to thank everyone for their questions and congratulate and thank our panelists for joining us. For those tuning in remotely, I'm looking at you, we will be live streaming this afternoon's Laudatios and next Thursday's closing ceremony on this YouTube channel. And we will also be posting recordings of ICM talks to this YouTube channel. So if you want to see those as they become live, please subscribe. Thank you again, and have a great rest of your day.